Well, hi everyone. Welcome to chapter 14 of our text. And there are three principal topics we're going to go through and review and learn about with regard to multi-criteria decisions. That meaning, of course, that you've set a more than one criteria for the basis upon which to make your decision. And there are these three techniques we're going to explore: goal programming, scoring models, and analytic hierarchy process. So first, let's explore goal programming. It's got some similarity to linear programming with objective functions and functional and constraints and so on. Some similarities to the things we explored in chapter 2. But in goal programming, we introduce the variables we identify with a D. We call them deviation variables, so that makes sense. And there are goals associated with them. In other words, we set kind of like a range, an upper and a lower limit that we're willing to accept. And we call those D1, D2, et cetera. The I here is usually reflected with some sort of number based on the priority goal. And we give it a superscript plus and minus, meaning the superscript meaning we exceed or overachieve with the goals, or the minus superscript meaning we underachieve or fall short of our goals. So we also use the goal programming methodology in terms of satisfying goals in a priority sequence. So we'll have priority 1 goal, priority 2 goal, and so on. Now, we can use the graphical solution approach to solving these types of problems, but they're only good for solving with two decision variables, just like we had in chapter 2. All right, so there is a nice example in our text that starts at page 690, and those objective functions that they express there in that example are something that you can refer to. I'm not actually going to go through it here in example, but I encourage you to read that, and I'm going to explain to you here what's going to be important for us to focus on. So as I remarked just a moment ago, we express objective functions according to priority levels, P1, P2, and so on, relative to minimizing or maximizing some deviation that I remarked upon earlier, D1, D2. So when we use the subscript D1, that's associated with goal P1. When we use D2, that's associated with P2. And that would repeat itself for 3 and so on. So when we use the superscript plus associated with that deviation variable, that represents the amount the solution exceeds the target value. I'll get to an example. And when we use the superscript minus, it represents how much we fall short. Now, the problems that we would work with in our examples usually have one functional constraint, and I'll explain what that is. So let's look at the process we would apply if we were using the graphical solution. I am not going to make you go through that for the exam, for the next test. You have done plenty of this for chapter 2. I have posted some example answers, and you will see a graphical solution, and then perhaps you'll also appreciate the fact that I'm not going to ask you to do that for the test since you've done it with chapter 2. But there are some similarities here. We plot certain constraints. We call them the functional constraints. We identify the feasible regions, and we plot the goal equations in order, and so on. And we use the deviation variables to identify where we're seeking the feasible region. You're not going to have to do that. So let's look at a specific example, and I will post more examples, and we will talk more about this in the next class when we review chapter 14. So I'm giving you a problem statement with an objective function and a set of constraints. Remember, with constraints we say subject to, ST, and the objective function here is to minimize something. That could very well be maximize something. So there are 5 questions that I want you to be able to understand and be able to answer. And the 6th, solving the problem graphically, you're not going to have to do that. So let's look at the answers to this particular practice problem. Okay, so I've given you the answers here. Let's flip back and forth. First question, what is the functional constraint expression? You can determine which is the functional constraint because the functional constraint will not have deviation variables. Notice that these two constraints have deviation variables, and they're also equality expressions. But functional constraints could have an equality expression as well. The key is to understand that these are not the functional constraints when you have the deviation variables. So if I ask you a question, what are the functional constraints? You would identify only those constraint expressions that do not have deviation variables. Therefore, the answer to question number 1 is that expression 9x1 plus 15x2 is less than or equal to 45. Okay, so then let's identify what is the priority 1 goal equation. Now, the goal equations are those constraints where we use equalities and we also have deviation variables. So when I remarked to you a few minutes ago with regard to the priority 1 goals, the deviation variables are also marked with a subscript that is an indicator of the priority. So subscript D1 means it's associated with priority 1. Subscript D2 means it's associated with priority 2. So the answer to questions 2 and 4 are very easy. Priority 1 goal equation is this: 8x1 plus 6x2 minus the deviation D1 plus D1 minus equals 24. The answer to question number 4, let's skip to that since it's of the same type. Priority 2 goal equation is this expression where we say equals 10. Okay, that is that expression. So I want you to be able to spot the goal equations for a given priority. And again, that's easy based on knowing that deviation variable expressions are marked with subscript 1s, 2s, and so on. Question 4. What is the question 4? What is the priority 2 goal equation? Again, that's indicative of the fact that the the expression for the goal here with the subscript in the deviation variables indicates that. All right, let's then get to the trickiest thing, questions 3 and 5. What are the priority 1 and 2 objectives? We need to be aware of the objective function expression. That's going to help us define this. And recognize that this is a min problem. Again, it could very well be a max. So let me show you the answer quickly and explain how we get that. So I want to use this language, and if I give you multiple choice examples, I will use this type of language. The priority 1 objective, and so on. So the priority 1 objective is to equal 24. We see that is to equal 24 while minimizing, because this is a min. If it were a max, we would say while maximizing. To equal 24 while minimizing the amount by which its D1 deviation variable causes it to, and notice up here in the objective function I have a plus, causes it to exceed 24. So let me repeat that. So the priority 1 objective. Priority 1 objective is to equal 24. You know that because of the D1 constraints, the deviation variables. That indicates that it's the priority 1 goal equation. Priority 1 objective is to equal 24 while minimizing the amount by which its deviation variable D1 causes it to exceed, we have the plus symbol, to exceed 24. So let's look at a slightly different example. Let's look at question 5 here. What is the priority 2 objective? The priority 2 objective is to equal 10. Why? Because the deviation variables D2 tell you that that's associated with priority 2. So the priority 2 objective is to equal 10 while minimizing, again, the min expression. If that said max, it would be maximizing. While minimizing the amount by which its deviation variable, D2, causes it to, what? Fall short when it's got the minus symbol. Fall short of 10. So that's what I've written here. And those are the types of questions that you're going to have to be able to answer for the test. You will not have to do the graphical solution because you've already done plenty of that with Chapter 2. I will give you some more examples. So let's continue to move on. Here's another example. So with regard to, let's look at questions 3 and 5, which are the trickiest, recognizing that this is our P1 objective, goal equation. This is our P2 goal equation. Okay, so priority 1 objective. Priority 1 is seeking to equal 30 while minimizing the amount by which its deviation causes it to exceed 30. Now, if that said D1 minus, the proper answer would be to fall short. But it's a plus, so it's exceed. Question 5, what's the priority 2 objective? Priority 2 objective is to equal 15 while also minimizing the amount by which its deviation variable, D2 minus, causes it to fall short of 15. And again, why fall short? Because you've got the negative symbol up here. If that had been a plus up there, you would say it causes it to exceed 15. Again, those are the answers here. Okay, so let's go on. Let's go on and talk about the second technique, scoring models. A very quick and easy way to arrive at a decision with multiple criteria when we understand the weighting or importance of those criteria. And we can understand what the outcomes might be when we have multiple options, such as what kind of car to buy or what type of computer to choose, and so on. Lots of different applications. I'll mention a real-world instance, that's something that I've done recently. All right, there are multiple steps involved, and you're generally only going to have to concern yourself with steps 4 and 5, okay? Because I'll generally give you data for steps 1 and 2 and 3, but you've got to create that generally from scratch in the real world. So we also have a mathematical model, which is very simple, where the score for any given alternative is given by the weight times the rating that it is given. But again, I'll give you an example. All right, so in the text, there was an example given starting at page 707 with regard to choosing a job and having an alternative for choosing a job and what the student would do with regard to having those options. So there are different alternatives going to Chicago, Denver, Houston, and so on, and there are different criteria: long-run career advancement, the location, the lifestyle, and so on. And those criteria are given weights, which use, in this case, a 5-point scale. You could use a 3-point scale, a 7-point scale, and so on. Whatever scale you want to use, different types of scales in the real world, including 6-point scales, so you don't have a midpoint. And then we assign a weighting. How important is something to us? And again, we're using here, in this case, a 5-point scale, but you can use different types of scales. And then we do a rating, and we decide the level of satisfaction. And again, multiple scale levels, 5, 7, 9, so on and so forth. Different granularity gives you different degrees of separation. You have a less opportunity to have to make conflicting decisions. So in this case, we rated the decision alternative for the different options based on career advancement. The Chicago job rated highly, more so than Denver or Houston, so on and so forth. And we did some math. We did some calculations for the Chicago option. We computed some scores and got some different numbers. And in this case, after computing those scores, we resulted in the accountant job in Denver having the highest net total. Right. So I'm going to give you an example, but let me quickly mention, this is some screenshots for something I did recently with a client of mine where we were evaluating requirements for a software system, and we had different elements that were being considered. We called them sub-factors. We had to identify what score they would be given. These green cells were made so that they could be edited on a 1 to 10 scale. We gave them priority ratings on a 1 to 10 scale. They had a total, and then we actually had 4 factors, each with multiple sub-factors. We gave them an overall weighting. We normalized that to a 100-point scale, and we made that. Pardon me. There we go. Bear with me, come back to that, thank you. And then we had a factor total to accumulate there. Thank you.